Medium data.
Welcome back to Perpetual Jank Machine, the podcast that does not talk a lot about UI jank, despite it being in the name. I'm John.
I'm Miles.
According to the rumor mill, this is not confirmed, I believe, AVX 512 will be taken out of Alder Lake CPUs. Previously, if you had certain motherboards, you could enable it kind of under the table. Intel previously said that they were not going to support AVX 512 with Alder Lake, and I don't believe it's validated by them, but the real truth is that you can just disable the efficiency cores, go into your BIOS, turn on AVX 512, and from all of the things that I have tried, it works perfectly, and I haven't noticed any errata yet. So it seems to be a perfectly functioning AVX 512 unit, and they're just going to get rid of it with new microcode, is the news, which I think is kind of disappointing, to be honest. AVX 512 has been much maligned over the past couple of years regarding problems about downclocking, problems about it not really doing all that much for performance while significantly increasing power draw, and of course, discussions about the die space that it takes up on the die. So I've done quite a bit of optimization with AVX and AVX 512 in the past. We're both quite familiar with how to build relatively scalable software and the benefits of optimizing.
Yeah.
And whether that may or may not be a good idea, especially in terms of getting features out on time and making sure that clients are happy.
Yeah.
Because if a civil engineer builds a bridge to last 1,000 years, then they have massively overspent. And the same goes with software. If you build the fastest thing in the world, you probably massively overspent on that feature 99% of the time.
But you had a lot of fun along the way, and that's what counts.
Unless you're on like NVIDIA's CUDA team.
Oh, yeah.
Like those guys, the MKL guys, those people have different incentives. But from a standard software developer's perspective, AVX 512 actually offers some very interesting things to people in our line of work.
Yeah.
So I just wanted to start out with a couple of numbers to kind of like quantify the benefit of using AVX 512 compared to just AVX2 with its 256-bit vectors and reduced instruction set. So I actually ran a couple of different benchmarks. One of them is Intel's own SVT AV1 encoder benchmark. Well, it's not a benchmark. I just used it like a benchmark. And this was with the Pharonics test suite. So we actually found that the benefit of AVX 512 is actually exactly equivalent to the benefit of the little cores on my 12600K. So that was about 829%. Obviously, this is not a program that responds particularly well to the little cores, but that was what we found. And I also ran it through a custom coded benchmark that I wrote just so I could better control the variables and actually understand what was going on here. And I found a roughly 7 to 8% improvement using AVX 512 like for like. So AVX 512 on just the big cores and then AVX2 on just the big cores. So that is a notable performance improvement. I think most companies would be happy if they were able to improve their general purpose performance by 8% year on year. And the elephant in the room, of course, is that not all workloads can use AVX 512. Some just don't have enough data to process, or some of them are just not coherent enough. But it does go to show that in a lot of real-world use cases, you can actually get a pretty sizable benefit from AVX 512, not just these artificial benchmarks that show like double the performance.
How does your artificial benchmark show that it works for not artificial benchmarks? Okay, I'm just going to throw that out there.
Well, I used one non-artificial benchmark for that. I think we want to put more weight on the SVT AV1, certainly.
Oh, yeah.
My artificial benchmark was just a basic implementation of threesum, which is a n-squared operation over order of n memory, so it is slightly flop constrained.
And a very useful problem.
If you are interviewing for some company that uses that, then yes, that will certainly get you some bonus points.
Do you just freaking drop the freaking hardware optimizations on the stupid problem?
Yeah, write out like _mm_ add PS on their whiteboard. I'm sure they're gonna love that.
Yeah. You're like, oh, what version of the GCC is this? Oh, it's a hypothetical GCC and it doesn't have. Oh, well, all right.
Wait, you're saying the whiteboard isn't a computer? It won't run what I write on it. Oh, that's a real shame.
But then why did it work for Git?
So yes, if you want to get some brownie points with that, you can certainly implement AVX threesum, and it is massively faster than non-AVX threesum, and AVX 512 offers further benefits to that.
What is massively faster in this scenario? You did the benchmark.
The theoretical benefit of AVX 512 just on straight line flop constrained code is, if you're working with characters, it's like 64 times or something stupid like that. But even in real world scenarios, you can see like, a 10 to 50% improvement depending on what you are coding. 50% is on the extreme end of that.
Okay, yeah, that's a lot. That
is not nothing.
No, that's a lot. That's a lot.
So we've quantified the benefits of it. Now let's quantify the cost. So I actually looked at some die shots of Alder Lake, particularly from nemez.net or at GPUs are magic on Twitter. And he actually labels the different parts of the core. So you can see like various parts of the front end, the branch predictor, the execution units, the register file, stuff like that. And according to his labeling of the SIMD unit and the vector registers, because AVX and AVX 512 use a lot of the same components, it actually determines that the AVX 512 unit was actually about a half to 2/3 of a little core's die usage, and that includes a quarter of the cache in that slice and its interconnect and all of that stuff. This is largely structurally shared with a lot of optimizations that we agree are good, like AVX and SSE. I don't think I've ever seen a single person say that SSE was a bad idea. Let's pretend that AVX 512 roughly doubles the size of the SIMD unit. Like it's about half the die space for just regular AVX. That's only like a third of the space of a little core.
Yeah. But it really strikes me as a weird change, considering everything's like about parallelization now. Now that like it's hard to get much better like single threaded performance, and this like it seems to be one of those things that does well. Like it's basically parallelizing like instructions. Yeah, so it seems odd that they're like we're going big, and then like eventually they're like, never mind.
It's weird because you would figure that AVX actually has like this unique trait where it exploits parallelism to make a single core faster. Whereas a lot of pieces of advanced computer architecture nowadays with, multi-core systems and heterogeneous processing, they don't do that. AVX 512, you could never touch another core on the system. And if you use AVX 512, your code will be faster because of that parallelism, but in spite of all the other resources that your computer offers.
Yeah. I mean, if you can vectorize it in that way, then you probably just as well get advantage from like multi-threading it.
That's true in some cases, I would say.
Well, I mean, what case would this work only for a single core?
Well, the cool thing about AVX and SSE and pretty much all SIMD operations are they do not introduce any overhead over what the base computation is. So if I want to encode like 100 bytes into base 64, AVX can do it without significant overhead because you are within the same instruction pipeline. There's no cache flushing. There's no context switching. There's none of that. If you wanted to spin up a different core to encode 100 bytes into base 64, you would have lost before that extra thread was even spun up by the operating system. You would have lost hundreds of times over.
Yeah.
And if you wanted to ship it off to a GPU, you would have lost thousands of times over at that point because that's going off chip.
Yeah.
But with AVX 512 and with AVX and SSE in general, there is no problem with that because it is within that same context. That's why it's so, I think, powerful, is that it's cache coherent and it is not interrupting what the CPU is doing at that time.
Wait, how many units does CPU have for 512? Or is it just one?
So within Golden Cove, it's 2 FMAs, 3 ALUs, and then 2 floating point adders. So it is superscalar, and that is actually reflected in Intel's Intrinsics guides. They will actually tell you, like, oh, we can do 3 of these per cycle. But the important thing is that it's within one core. That's the cool thing about this, is you can have one core in a really hot loop, and you can switch over to an AVX code path with almost no penalty. Because you're reading from the same memory, you're writing to the same memory, and there's no problem with caching.
It's all in cache already, baby.
Yeah, precisely. It's really uniquely positioned in that it takes advantage of parallelism while not incurring the same problems as multi-threading. So I think that it is actually a benefit to have like a big SIMD unit in terms of single-threaded performance, because single-threaded performance is much harder to attain than multi-threaded performance nowadays.
Oh, absolutely.
Because with multi-threaded performance, just slap another 8 cores on it. With single-threaded performance, you need to really whip out the brains.
But if you're already packaging up data like that, if you can package up, if you have the luxury to do that and it's not like sequential, then oftentimes it is something you can offload to multiple cores and stuff like that. And yeah, you incur some overhead, but usually it's not that big of a problem if you're doing that much. So I think what you're saying is where this really shines is like medium-sized things, which strikes me as really odd. Yeah.
It really does. It's not something that's going to make your 2048 by 2048 matmuls any quicker than, you're already getting with your vector processor off chip.
Yeah.
But the fact that it is useful for those medium-sized tasks means you can use it in lots of workloads that you wouldn't think as acceleratable by, for example, a vector processor or multiple cores usually. So you can use it for base64 encoding, you can use it for JSON parsing, you can use it for all sorts of different workloads. I think there's like HTTP servers that use it, lots of codecs use it. Video encoding is something that can be accelerated by multiple cores, but within those cores, they each have a SIMD unit, and you can take advantage even further of the data parallelism with that.
Yeah, you really get a lot out of it, specifically for things that are like, I don't know, like 512 bits long, something like that.
That actually launches into another thing, and that AVX512 is not just a doubling of vector sizes, which I think is something that is somewhat misunderstood by a lot of people. SSE and SSE2 are 128-bit extensions, as are like SSE3, 4, 4.2, whatever. AVX is 256-bit, but AVX also added additional operations on top of SSE and SSE2 and whatever. But AVX512, in addition to doubling the vector size of things, really goes all out with making it much easier to write vector code by giving you so many more tools to work with. It's not just like, it doesn't just add AVX again, but with 512-bit vectors. There is so much more to AVX512 than just the doubling. And that makes it a lot easier to write programs as well for vector stuff. So you and I have discussed in the past a lot about the benefits of optimizing things to be high performance versus the downsides of that, and that it takes up more programmer time, which in turn costs your company a lot more money. So your and my thoughts on that may differ a little bit. I'm very pro-bloat in a lot of cases from the perspective of a programmer, and some people may disagree with me over that, and that's completely okay. But the fact that AVX512 adds so many of these operations to make it easier for a programmer, I think is really powerful, and that it empowers more people to actually use these operations. Yeah,
because all you need is like data that can be like a big chunk. That's pretty much the only requirement. It's like a big chunk of data.
Yeah, and previously, like in past versions of AVX and SSE, like it had to be regular data. Sometimes it had to be like, well, it doesn't have to be anymore, but it used to get benefits out of it being aligned. If it was like maybe half data that you cared about and half data that you didn't care about, that was when you really started to see feasibility problems with, how do I implement this in a way that's fast? Because previously you like didn't have great ways of shuffling data around. But now with AVX512, it has so many of these instructions that make dealing with irregular data so easy. It really is like just leaps and bounds, and you can actually implement many more things quicker than you could with scalar code that previously I don't think were easily possible.
Wait, does that have to do with this masking instruction? Because you were talking about that.
Masking is certainly part of it. There's also just functions in there that make it easier. Like I'll go through a couple. For example, let's say that we have an array that's 37 bytes long, and I have a 512-bit register that can pick up 64 bytes at a time, right?
Yeah.
If I don't use masking, so in the old way that AVX2 and SSE forced upon you, you would pick up with AVX, you pick up the first 32 bits in the first register, and that's all hunky-dory, and you can do whatever you want with that first register, right? But then what about the remaining 5 bits? If you try to access all of them, you might run over the amount of memory that you have allocated for your array, and then you're going to have problems, right?
Yeah.
You might run into another page, and that's going to cause all sorts of problems. You're going to seg faults in some situations. So what you can do with the mask registers now is you can actually say, hey, I want to load in these 5 bytes of memory, but don't do anything else for the remaining, 27 bytes.
Yeah, that is nice.
I can just load in those 5 bytes, do whatever I want to them in my SIMD computation, and I don't have to worry about crashing my entire program just because I wanted to get a little bit of extra performance.
Yeah.
Whereas previously what you had to do was like this weird trick with like, you did like an unaligned load, or the data might have been aligned just by chance, but you usually did like an unaligned load, and like the data was like out of order in the thing because you actually had to like backload some of the array, and it was a mess. Or you had to write like a scalar tail to it. So what you would do is you would have a vector code path, which was nice and fast, which did like the first 90% or 99% of the array. And then for that last 5 to...
That last little bit, you got that if statement.
Last 5 to 31 byte thing, you would load it in a scalar thing. And that was like a whole other block of code that you had to write and you had to test for. So it was really annoying. But now you don't have to do that. It can just be one vector code path. And that's so much easier on the programmer because
it's beautiful.
It's literally half the code that you have to cover in your test suite. Like, you don't have to do any of this, like, oh, it works on 32-byte arrays, but it works on 33-byte arrays too, but it also works on 31-byte arrays. So you can just say it works. That there's no more like special casing or anything like that. So that's huge.
People love to talk about that big data, but let's talk about that medium data, you know?
Like simple operations on medium data too. And, there's just so many other operations like this where there's like reductive compressing and expanding of data now. So like, let's say that you have data that you care about in index 3, 7, 10, 12, 16, 24, and 39, right?
Mm-hmm.
Previous versions of AVX, like, good luck figuring that out. You're going to have to do some kind of like special, effectively magic, because there was no good permuting in AVX2. Like, the best you could do was 32-bit words across lanes. Now with AVX 512, not only do you have a full suite of permutes, but you can actually have these special instructions that pack all that data that you care about together. And that's not the most efficient thing in the world, and I'm not going to pretend that it is, because if you're only packing together like 6 things that you care about in a 64-byte array, that's not going to speed you up all that much. But it still opens the door to maybe operating on 6 elements at a time rather than operating on 1 element at a time, or 3 or 4, depending on how well your out-of-order execution can handle it. And that's huge, right? And not only is that a potential speed gain, it's also a understandability of the code gain. Because previously you had to do like all this black magic nonsense. Like, you can go and read about, I think it was like Wojtek Miła's like base 64 encoding, and that's using AVX 512, and it still has to do some like weird arcane bit shifting and stuff that's really hard to understand. Like, imagine if you had to do that with AVX. That'd be even more arcane and even harder to understand. So I think it opens up a lot of doors for mortals like us to write fast code effectively.
Yeah.
And the cool thing is that all of this is backported to the 128-bit vectors and the 256-bit vectors too. So let's say that, unfortunately, if you remove AVX 512, you remove all these nice instructions because of the way that it's delineated. But if I, for some reason, want to use 256-bit vectors because like I have concerns about downclocking or something, because I'm using like an old Skylake chip, I can do that. And it can still be this really nice, well-written, easily understandable code path. And if you don't require like a gazillion flops, if it's more memory bottlenecked than flop bottlenecked at that point, then you might not be losing anything from that, which is really cool. So it really helps programmers understand what they're doing as well, which I think is like something that's hugely overlooked.
It sounds like it simplifies a lot of stuff, and then it's just going to be gone. And yeah, like what you said, it really makes it strange that it kind of makes it so that way old processors can just do something that a modern processor can, and that would be really odd.
Like, a big problem with this is the old Rocket Lake and the Tiger Lake chips that are out right now and that you can still buy, they work perfectly with AVX 512, and
like, backwards compatibility is an issue, and then suddenly like forward compatibility is going to be an issue. It's like going to be like Python 3 with people trying to port their Python 2 code. It's
this cruel stroke of luck that AVX 512 is not that well implemented and understood in a lot of places, that they're going to be able to get away with this without any forward compatibility problems whatsoever, probably.
Yeah.
Because everybody who has an AVX 512 code path right now probably has an AVX2 code path as well, and they certainly have a C code path regardless. But yeah, it's just so profoundly like strange. Like, I was expecting Alder Lake to figure out how to run AVX 512 with the little cores enabled, and I was perfectly fine to disable them to get AVX 512 working. Like, there wasn't time, that's fine. But now to take it away from a chip that has it working perfectly well is just really strange, because let's say that there is like theoretically some program out there that was compiled for AVX 512 and it has an AVX 512 and a C path. And like, maybe it's not open source. Like, what are you going to do when you upgrade your system and you realize that program doesn't work? Like, you can use the C code path, sure, but then it's going to be slower on the new chip.
Yeah, and if you're doing 512, then you probably need something to go fast. Like, that's not something everyone's enabling.
Yeah, and it's not even just fast. Simmed computations are notorious for being very power hungry, but power is not necessarily equal to energy consumed. If you have a high power consumption over a short amount of time, that can still be more efficient than a low amount of power consumed over a long amount of time as well.
Yeah, sometimes. No, usually stuff gets hot, and when stuff gets hot.
To limits, certainly. But if you're 50% faster with AVX 512 and you use 30% more power, yeah, you
25% more, yeah.
You still win.
Net gain, buddy.
Yeah, it's environmentally conscious.
We haven't run the numbers on that one, so don't quote us on that.
And then, like, further compounding this weirdness about compatibility is that this wasn't part of, I think, Tiger Lake or Rocket Lake chips, but they have hardware support for floating point 16, which is 16-bit floating point numbers. And if you want to use those with any kind of computation, really, you're probably going to need to enable AVX 512 to actually get those working, because otherwise you're going to need to like download a software library for FP16, most FP16 is like done on adding cards and is usually used well above our pay grade, but I think that there's a lot of potential for FP16 for like workloads that don't necessarily need a lot of precision and also need a lot of speed that are not big data. And removing it just removes any potential for adoption. Like even if it comes out in next year's chips and it's supported, that's another year you're going to be waiting for it to trickle down into stuff that we can use.
Yeah, it's just weird. It's a weird thing. I don't know. How many people do you think realistically use this? Like this probably was sitting on like most chips, probably doing literally nothing. If we're gonna be honest.
Once something is released, it needs to get adopted by programmers, and then it needs to be made easy for users, right?
Yeah.
And AVX 512 was only out for a couple of years before then in like consumer chips. So there was one generation of Intel consumer chip that supported it, and I think 2 or 3 generations of like really expensive enthusiast chips that supported it, Skylake X. So you get like 1 year of it existing, which is definitely not enough time for it to really percolate out into the mainstream. So we've seen programs consistently gain more and more vector optimizations over time. Like things are still getting AVX code paths to this day as we speak, and AVX was released in 2011, something like that. So I don't know if judging something that recently released by like its first couple of years of adoption is necessarily like a fair metric for how it'll shake out in the future. But most things that used it were benchmarks, like Intel's own software like SVT uses it pretty extensively to my knowledge. And, you know, stuff that you would write yourself as, you know, benchmarks and stuff like that. And, you know, there certainly were academic libraries like that used it. Like in the same way that there are libraries that can parse JSON with AVX, a lot of things don't use those AVX accelerated libraries. They're just sitting on Daniel Lemayere's GitHub, you know, waiting for users in some cases. Certainly not in all cases, but, you know, there are lots of languages that implement their own JSON parsers, for example.
Yeah.
Which is really a shame because Daniel Lemayere is absolutely brilliant and his source code deserves to be in as many places as possible.
Yeah. I think a bit of the problem with it is it's not too generally, like, it seems hard to implement it, like, for something that would be higher level. Most things that get programmed are like things that get built on top of things that get built on top of things. So the only way it's going to see use is if something pretty core to the many things that are building on top of it adopts it and starts figuring out a good way to use it. And I don't know how common that was.
Most browsers have some degree of simmed acceleration. Like, for example, you know, we could take that base64 example from earlier. Like, a lot of sites serve their images, even though this isn't the best way of doing it usually. Some sites, like, serve somewhat large images as just base64 data URLs. And they take a non-trivial amount of CPU time to, like, unencode, parse, and then render. So I am not a master of image encoding. I have not written an image encoder, but I imagine that image encoding is something that certainly could benefit from wider and wider vectors.
Yeah.
So Amdahl's law, you know, you make the image encoder really fast and you make the renderer really fast because it's on a GPU. There's still the encoding time. And although that's just basic ON data encoding, why not make it a little bit faster? Why not make it the speed of your memory rather than the speed of a single ALU in your CPU?
Well, I mean, at that point, usually it's more the speed of your download speed. That's usually the limiting factor, if we're going to be honest.
Well, it's added on top of that, too, so.
Yeah. Yeah. I guess so. If I've had a image... if my image is stalling to load, there's a very low chance I'm going to blame my freaking CPU.
Well, some things can take a little bit of time to parse. Like those die shots that I was checking out, those took some time to download, but it also took a little bit of time to scan down and display.
Yeah.
And those were many megabytes large, but
I don't know.
You know, many megabyte large images are not necessarily out of the domain of a standard user. Like you can want to download a photo that was taken by a DSLR.
Yeah. Well, I don't know. Does the freaking JVM use it a lot? I don't know.
The JVM has some auto-vectorization. I think that Clang and GCC are probably the best examples of, well, really LLVM and GCC's backend are the best example of auto-vectorizers. But if you really want performance from AVX 512, you need to write it by hand effectively.
Yeah. Which I think is where the lack of use comes from.
Yeah, and It just comes back to the fact that software engineers are busy and they make a lot of money. So it's really difficult to say, okay, you can take 3 months to go do that.
Yeah, it's the problem is it's in a consumer chip. It's hard to justify something that is going to be used by pretty much just specialty cases for consumers.
I don't think that it's necessarily a specialty case, though, because, image encoding, base64 decoding, video encoding, these are all things that we can expect average users to do. Like, I'm looking at an image right now.
Well, I mean, I think it's more like people who, like artists, people who do stuff like, actually editing images in like freaking, Photoshop, stuff like that.
Mm-hmm.
It's hard to justify where the average everyday consumer is getting a lot of mileage out of this. Like, I hate that it's being removed. What I'm saying is I kind of understand the choice as Intel, like from Intel as like a company.
Well, okay, think of it this way, right? libpng, this is the library that everybody uses to parse PNGs. That's, if you see a PNG image, you are running libpng.
Yeah.
So libpng offers SSE optimizations. And presumably, if it works with SSE, it's going to work really well with AVX, right? There will certainly be some small benefit to enabling either wider vectors or potentially using these new operations. Like, let's pretend that it's maybe like a 5% gain at a very conservative tack.
Yeah.
If every single PNG parsing and encoding ever was made 5% more efficient, can you imagine how much energy and how much time across the world that would have been saved?
But how much work is relying on a PNG to like encode and decode? Like, once again, like usually the limiting factor for that is something online. If you are loading an image directly from your hard drive or something like that, it's not really like, it's pretty much next to instant. Like, nobody really complains that the PNG isn't loading from their photos file.
It's next to instant, but it's done so many times. That's the thing. A small number times a huge number of occurrences is still a reasonable number, I'd imagine. Especially when you consider like energy use, right? Like, let's say that you go onto Reddit and you scroll down a little bit. How many images at what resolution did you just load, right? How many CPU cycles did you just use?
Yeah.
Multiply that by 1 billion people every day.
Okay, yeah, Mr. I love bloat, freaking saying that the PNGs are taking up too much energy. We gotta shut them down.
Well, that's what I'm saying, is that we've done this with video before. Like, we've implemented hardware decoders for video, because if you decode a video on a CPU or even on a GPU, really, it uses way too much energy. It kills batteries.
But people are watching video like 24 hours a day. Like, people are watching Netflix all day. That's a real thing. Nobody's looking through photo albums all day. That's not a thing.
Are they, though? The web is effectively a huge photo album.
Okay.
Let me go into youtube.com right now, and I'm going to tell you how many images my browser parses.
Okay.
It pulled down 1.43 megabytes of images over 60 requests. So that's 60 images that it tried to load.
Okay.
I think that's a good case, right? These are small images, yes. But again, if we made it 5% faster for however many hits YouTube gets per second, that's a lot of energy saved.
True.
And that's a lot of performance that you claw back. And again, it's not just the encoding of one image. If you go onto Netflix or something, you're going to see preview images for shows, and it might load in multiple preview images at once. Okay.
But if you're on YouTube or Netflix, you're probably there to watch a video. And video encoding is obviously...
But then I go to a new page every 5 minutes or 10 minutes for a new video, and then my recommendeds show another, 10, 20 images?
Okay. And YouTube videos are shorter.
And this is so widely applicable, and AVX 512 improves on the situation to such a high degree, not just with raw teraflops, because I don't think that the flops are the problem here. It just makes it so much easier and so much more accessible. And it also makes it so much more possible, where you can now write something in one instruction that would previously take 3 very difficult to understand instructions, that I think is a huge benefit, honestly.
Yeah.
I'm really glad that it was included over another, I guess, 2 little cores in this case. I would take it over 2 little cores.
I mean, if we're going to be honest, half the time the cores are sitting there doing nothing, most of the cores. So I guess it's not that crazy to say that just because this is sitting there doing nothing for a good portion of the time doesn't mean that it isn't valuable for the time that it is used.
And I think that a lot of people think about the code that is not performance intensive. The vast majority of code, probably more than 99% of it, is not at all a performance bottleneck in any sense of the word, right? We're talking about these little gadgets, right? We're talking about base64 encoding, image encoding, video encoding, 3D rendering, CSG, HTTP stuff that might be, at a gazillion requests per second. And we talk about that, and that's only a couple of use cases, but like, what else are you using your computer for, right? Like, if you're using it to browse and send email, then you are perfectly fine on a Pentium 2 still, presumably, assuming it's still secure and still supports the latest whatever.
You probably don't care about security if you're just doing text editing.
Yeah, I guess if you're just doing text editing, you wouldn't even know about it, but...
It's at the forefront of their mind.
And that's perfectly fine, but the reality is that none of us are buying A53s anymore. None of us are buying, Cortex A55s because...
Marketing.
Well, yes, marketing for most people, but a lot of people have things to do and they want it to be done in a reasonable amount of time. And those things to do are things that can be accelerated by SSE and AVX and AVX 512. And if AVX 512 only gives us another 8%, that's great. I'll take another 8%.
Yeah.
And especially because a lot of these instructions, they use existing hardware. The FMAT and the FM sub are not two separate ALUs and two separate FMA units, and the mass registers are overlaid on the x87 registers, at least on Skylake from what I've seen. And I can't imagine that they would do separate registers otherwise, because nobody's using AVX 512 and MMX anymore, or x87. So, Intel engineers are really smart. They can reuse hardware in really creative ways. And, just the fact that, I don't have to write, these, 64-byte chunks of memory anymore, memory patterns to do these things that I want to do with AVX. That's huge. That's really, really huge. And I'm really surprised that a lot of people don't appreciate it, because people croon over 10% single core efficiency gains, and AVX 512 can give you a 10% single core efficiency gain on most of the workloads that are CPU constraining workloads.
Medium data.
It's never going to accelerate email, but nobody needs email to be accelerated anymore.
Yeah. That's not really an issue. Yeah, and
maybe it can accelerate parts of the email protocol. Not that we care, but it probably can. If it can accelerate HTTP and JSON parsing, you don't think it can accelerate IMAP?
It's weird that they're taking it away, and they're not going to give it back. That would be even weirder decision to take it away and then be like, oh, that was a mistake. Here, you guys, you can have it again. That would be weird. So that they're pretty much just done with it.
Yeah, I don't know what their next move is going to be honest, because I think AVX 512 is a good forward-looking ISA extension. I think it's the best one since SSE, to be honest, or SSE2. Probably SSE2, because that added int. But the thing is that if you read an article on OnTech, I think, they said that it was planned to come out, maybe if you disabled the efficiency cores, but it was planned to come out, and then it was just taken away at the last moment, and the engineers were really not happy about it, which makes sense, because I'm an engineer, and I totally sympathize with that.
Yeah.
So I don't understand why they would do it. I imagine for that reason, it was for some kind of business thing, or they didn't want to validate it or something, but that doesn't make sense because they validated it for Rocket Lake. They validated it for Tiger Lake, and removing it doesn't have a business advantage because their competitor doesn't have it. So it's something they can lord over their competitor, and they can just slam them with SVT scores that are 8% higher than they would otherwise be. So yeah, I don't get it.
I'd imagine it's because they're already struggling. Because, I don't know, aren't they having trouble shrinking their stuff anymore?
I heard that they solved that for the most part. Alder Lake is on the process that they were having problems with, and from my experience, it is a very solid, software notwithstanding, it's a very solid process and a solid chip design. But God, just open it up, why not? You can say that you don't validate for it, sure. Just have everybody include a warning in a BIOS, you can already, if you're dictating that they should take it away, I'm sure that they're equally powerful to dictate, this must show a dialogue saying this is not internally validated at Intel, and we're not going to publish any errata on it, and we're not going to publish docs on it, which is fine, because we're programmers, we'll figure it out.
Yeah, it's sad. Well, if you get a little more die space, you can put another core on it, and whenever you compete against AMD, who's just chucking out cores they're nobody's business, maybe that's what they were thinking. We could put more cores on, even if it's a little core. Even if it's a little core, it's a core.
Yeah, but they're taking it away when they've already put it on the chip.
Cores sell CPUs, bud.
No, but they don't gain anything from this because they've paid for the AVX 512 unit on every Alder Lake chip that's ever going to come out, presumably. If they're paying for it, if they're putting it on the chip, this doesn't preclude them, spinning up another version of these chips that doesn't have the unit on there, but I don't know why they would add it in the first place if that were not something that...
Well, why would they disable it if they were planning on keeping it? That doesn't make any sense either. I think it's safe to assume it's not going to get stamped onto any future model.
That's part of why I made this topic, why is AVX 512 good, rather than why is software locking something bad? Because presumably this would be for some kind of long-term strategy or for some kind of business or product segmentation reason. I've heard, those being brought up. I don't think product segmentation would make sense to me, because like, who's going to buy a 12600K that would otherwise buy like a Sapphire Rapids chip, right? Like that.
Yeah.
Nobody in their right mind is cross-shopping those two chips, but that's beside the point.
Security that you don't have to worry about.
But it's the same core. Meltdown hit both my buddy's 8700K and it hit the Xeon Platinums or whatever the heck they were using back then. It's like the same exact...
Yeah, but you don't have to worry about a vulnerability with it. If somehow someone figured out something, if they needed to like software patch anything, then they don't really have to if it's already gone, and they don't have to keep testing it to make sure nothing's breaking if it's already gone, hypothetically. That's like the only reason I could come up with, but it's not a very good reason, if I'm going to be honest. Like they're spending a lot more money on other things. I would imagine that's not like the end of like their biggest concern. Like, don't overclock your CPU, but you can. But like, don't do it. Don't do it.
Why are they releasing K-SKUs? Why are they releasing XMP? This is the exact same level of gray area, I think, except this one is so much more technical. It's not even the stuff that would make it into like, the 10 tips to make your computer faster videos, right?
Flip on. Did you know your computer can crunch twice the size of numbers? Yeah, just flip it on, bud. Your PNGs are going to be blazing after this.
Do you have any idea how much energy you're going to save?
A little bit.
Or not, depending on how your chip is architected.
Program with it while you still have the chance. Because it is fun. It is fun to do vector stuff.
It really is.
Yeah.
It's like a whole different way of thinking, and it really will expand the way that you think about computers. And that's the show. Thanks to Meydän, that's Meyda with an umlaut N, for their track The Beauty of Maths, licensed under the Creative Commons Attribution 3.0 license, which serves as our intro, outro, and interlude music. You can find more in the description of this episode. Please remember that the opinions expressed in this production may not reflect those of other participants on the show, or those of any participant's past, current, or future employers. They're also probably exaggerated a bit for comedy's sake. Anyway, thanks for tuning in.